Okay, so today is September 14, 2021, and let's take a look at the slides here for the vectors. So we are going to make a quick review. Okay, there is one another thing that I didn't cover, and I'm going to cover right now. Here you go. That's how you represent a vector. You represent a vector with as an arrow, and the name of the vector is a letter with a symbol there at the top. The magnitude of the vector is the length of the vector, and the direction of the vector is the angle. Okay, so vectors A and B, even though they are placed at different spots, they are equal because they have the same direction and the same magnitude. It doesn't matter whether they are placed at different spots, provided their direction and their magnitude are the same. Okay, so here vector B has the same direction, but has a different length. So they're different. Those two vectors are different. And in the case of vector B, magnitude of B is greater than the magnitude of A. Okay, so here go different vectors, vectors minus A, vector C, B, and so on. If you can multiply a vector with a scalar, if the scalar is greater than 1, the vector is going to become longer. Okay, and that's the vector E, the direction doesn't change. If the scalar is less than 1, greater than 0, then the vector is going to become shorter. That will be the vector S. We covered that. You can divide as well by a scalar. If you're dividing by a scalar that's greater than 1, the vector becomes shorter. If you divide by a scalar that's less than 1, the vector becomes longer. Larger magnitude, but same direction. Okay, so operations here with vectors. Here you go, I'm dividing by the scalar 2, multiplying by the scalar 2. I can multiply also by the scalar minus 1, and the vector just changes direction. Nothing else but changes direction. Question the slide. Let's see, from current slide. Let's get that. Yeah, here you go. Better now, right? So here you go, vector minus 2a. Change the direction, change the magnitude as well. The previous one, it just changed the direction, didn't change the magnitude. The magnitude of this vector here is the same as the magnitude of this vector here. Okay, that's representation in the three-dimensional space of a vector, x, y, and z axis. And then we can draw in such a way as so you have this illusion that the vector is sticking out from the plane of the computer, right? Operation with vectors. You can sum vectors. Summation between vectors, a plus a. You get 2a. And how do you determine the resulting vector? You can use the head-to-tail method. The vectors are different, but the direction is the same. And the magnitude is different as well. Okay, head-to-tail method. Here you go, head-to-tail method. You have a and b vector. You put the tail of the b next to the head of the a, and the resulting vector is going to be a longer vector, c, a plus b. You know, you can also have b plus a. Here you go. Okay, b plus a. B plus a is what? You put the tail of the a on the head of the b, and you still get the same vector. Same length, same magnitude, same direction. Okay, so here you go. C, a plus b, b plus a. Okay, so summation is a commutative, has a commutative property. Vector, when you sum two vectors, you know, the sum of the vectors obey the commutative property. Okay. Okay, the magnitude is going to be the same. When the summation of the vector is one-dimensional, in the same direction, okay, the magnitude of the resulting vector is going to be the magnitude of one plus the magnitude of the other. But only whenever the vectors are pointing the same direction. Okay, though that's what we call summation between one-dimensional vector. Now you can have two vectors at different angles, different directions, different magnitudes, right? And when you sum those two vectors, you're going to get a resulting vector using the head-to-tail method. Okay, mathematically speaking, here you go. That's the head-to-tail method. What I didn't tell you last time is that, you know, you can have a relation here. You can determine the magnitude of the C vector just by using the cosine law. Okay? So how does the cosine law looks like? We can prove that mathematically. Okay, so suppose that we have a triangle, right? Like that. Here's the length A, here's the length B, here's the length C. And here's the angle alpha, opposite to the side A. Here is the angle beta, and here is the angle gamma, opposite to side B and side C respectively. It's easy to remember the cosine law, okay? You already know if you have a right angle triangle, right? If you have a right angle triangle like this one, you have this relationship. You know that, right? But what about if the angle is not 90 degrees? Okay, it's kind of similar. Let's put here, let's put this one A. Make it consistent. A C squared plus B squared, right? So the relation here is similar to this relation here. But because it's a different triangle, it's going to be a little bit more complicated. The equation that you're going to get, don't forget, is the cosine. We call it the cosine law. It's not a law, okay? But we call it a law anyway. So the relation is what? A squared is going to be B squared plus C squared. Make sense? Okay? Just like the Pythagorean theorem. Just like the Pythagorean theorem. Then you are going to end up having an additional term because this angle is not 90 degrees. So what you're going to have? You're going to have a minus sign. You can prove that twice A, B, okay, is a minus cosine of the angle alpha. Okay? Cosine law. But don't forget, it's always the opposite angle. If you want to calculate B squared, again, we can prove that it's going to be something like that. Okay? And the other plus B squared minus 2AB cosine of gamma. Okay? Those are the relations. They all look alike. If you're not sure it's a negative or positive, you can look at the special cases. Okay, you can look at special cases. If in case you're not sure it's positive or negative. You know, sometimes I forget, is that a positive or negative here, right? Then I make a simple test. Okay? If it's 90 degrees, if the angle here is 90 degrees, this term must be 0, right? To reduce to the Pythagorean theorem. Make sense? But it doesn't make any difference. No, alpha 90 degrees is going to be 0. Cosine of 90 degrees is going to be 0. Okay? So it doesn't help you to figure out whether it's a negative or a positive. In order for you to figure out if it's a negative or positive, what you got to do, you test it for alpha equal to 180 degrees. Okay? Test it for alpha equal 180 degrees. Here you go. Cosine. Cosine circle 0, 1, 0, minus 1, right? And 0. If the angle is 180 degrees, what does it mean? It means that the resulting length is going to be B plus C, right? Think about that. This guy moving down like that, you're going to get a resulting side, that's going to be b product plus c, right? Can you picture that? Just do a, here you go. Make this angle alpha go to 180 degrees. Okay, your resulting side A is going to be exactly b plus c. Okay, and let's see if it works. You replace here, a special case, right? A special case. Special case. Remember, this one is not being recorded, right? So you gotta take notes. Certain things you have to take notes, okay? Special case, alpha equal 180 degrees. A square equal to b square plus c square minus 2ab cosine of 180 degrees. Cosine of 180 degrees is minus 1, right? So what you get, b square plus c square minus 2ab times minus 1, right? And then what you get, b square plus c square plus 2ab, right? Which is equal, oh, wait a minute. Sorry. It's not ab, it's bc. It's bc here, okay? bc. ac, ab, yeah, bc. Fix that. bc, 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 okay? Fix that. So what you end up getting here is going to be b plus c squared, right? And your A ends up being equal to b plus c. Okay, special case. If you're not happy with just one case, you can do for alpha equal to 0 degrees as well. And you're going to get A equal to minus b minus c, right? 0 degrees means that the side C is going to go this way. Okay, and you have two vectors, right? Here you go. One vector like that, one vector like that, another vector like that. 0 degrees. One vector is going to subtract from the other one. You're going to get b minus c. Okay, because cosine of 0 degrees here is going to be 1. Okay? So that's what I didn't cover last time. Head-to-tail method, here you go. There is the parallelogram method that I mentioned to you as well, right? Here you go. You just draw a parallelogram. Okay. And then we're going to talk about the components of a vector. That's a far more powerful technique. In the case of the components of a vector, it's closer to the situation, to the parallelogram method. It's closer, okay? But it also can think also in terms of the head-to-tail method as well. So components of vector. So what do I mean by components of a vector? A given vector can have 2 or 3 components, which are going to be parallel to your x, y, and z axis. That's what it's all about. You can decompose this vector into either 2 components, in the case of 2-dimensional space, or 3 components in the case of the 3-dimensional space. Okay, so how can you visualize that? You can visualize that in terms of the x component of the vector. See that? And then the y component of the vector. You project, what are you doing here? We are projecting the vector along the x-axis and projecting the vector along the y-axis. Okay? It's a very useful way of representing a vector. Very, extremely useful way. Okay. And here you go. Here are the 2 components. And if you pay close attention, you can see that those two vectors are, if you apply the parallelogram method, when you sum those two vectors along the x and y axis, you end up with the vector A. See that? Okay? So here you go. Here's the parallelogram method. Right? But you can also think of that in terms of the head-to-tail method as well. Those components are a sum of the actual vector, either using the parallelogram method or the head-to-tail method. Either way. Okay? So just a reminder, if you want to really understand that, it's very important that you write that down too in the paper there. It's far, we managed to capture the idea far better if you pay attention and write down at the same time. Okay, just advice. Here you go. Oh, what else do we have to know? Okay, in order to, instead of just defining this vector in terms a sub y, right, vector a sub y and vector a sub x, there is another convenient way of defining those vectors. We can define that in terms of two unit vectors. One unit vector along the x direction and another unit vector along the y direction. Those unit vectors has no unit whatsoever. Okay? They are not measured in meters, they are not measured in kilograms, they are not measuring in anything. Their unit is 1. Okay? But the length here will have a dimension. This length here will have a dimension, a sub x. Let's see if I have, okay, here you go. Magnitude of, here's an example, okay? I have the x component of the vector A is 2 meters times the unit vector x. Unit vectors are usually represented by a hat there at the top. Unit vector x direction, you write down the x and the hat there at the top. Many books prefer to use not x hat, but I hat. Okay? I for x, j for y, and k for z. I, j, k, x, y, z. Many books prefer to do that, to use I, j, k. Most likely you saw that in math, right? I prefer to use the x and y, z, okay? Because it brings you back to the actual direction that you're using. And it's funny because whenever you're in undergraduate school, your math professor, your physics professor, they always tell you your vectors in terms of I, j, k, always. But then whenever you go to graduate school, they start to use not the I hat anymore, they start to use the x hat. Isn't that funny? Instead of starting with the x hat, y hat, z hat from the very beginning, no, they start with I, j, k. I prefer to use the x hat, y hat, z hat. Okay? So here you go. And don't forget the vector A in the x direction, in this case is 2 meters in the x hat direction. Okay. And the y component of the vector A is going to be 3 meters long. Because this guy is remember, because this guy is a vector, whatever goes on the right side must be a vector as well. So what you have here is a scalar multiplied by a vector. Okay, a unit vector. You want to know, suppose I give you the lengths of those two, the components of this vector, the two components of this vector. If I want to find out the lengths of the vector A, what do? All I have to do is to use the Pythagorean theorem. 4 squared plus 3 squared, plus 3 squared, which is 13. Make sense? Okay? So here you go. I'm gonna put here in the drawing, the board. Vector A can be decomposed as being a 2 meter vector in the x direction and a 3-meter vector in the y direction. That's the A vector. This one is A sub y vector, the A sub x vector. What's the length? What's the magnitude of the A vector? We have a theta angle right in here. Okay. So all you gotta do, magnitude of A is equal to the square root of magnitude of A sub y plus, remember, magnitude of A sub x. Or even better, let's switch. I didn't do this step by step there in the PowerPoint, right? A sub x is going to be 4 meters squared. No, wait a minute, let's put step by step, right? 2 meters here squared plus 3 meters here squared. Right? Pythagorean theorem. And that is 4 meters squared, 9 meters squared. We get square root of 13 meters. That's the length of this vector. Okay, so we have another example here. x3, x component 3, y component 1. If you're going to sum those two vectors, how do we do? How do we sum those two vectors in terms of the components? All we have to do is to sum each component separately. Okay, so here you go. By component sums up with the ay component. So the resulting vector c is going to be 4. The y component of the vector c is going to be 4 units. Should be meters, okay? I didn't put meters here. I gotta fix that. Let me take it out. Here you go. Meters. 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 It's gonna be meters as well. And the other ones too have to be meters. What was missing? Okay, this one I didn't miss, right? But this one I missed. Meters. Gotta put the unit there. Meters. Go. Meter. 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 And meter. Here you go. Next. Okay, so here you go. B plus A, we get this resulting vector C. The C vector is going to have a y component that is equal to 3 meters plus 1 meter, and an x component at 3 meters plus 2 meters. Let's see if we have it. Yep, right in here. I'm decomposing. Oh, let's put it. Meter. 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 And meter. Right, so here you go. Head to tail. See that head to tail method here? Bx plus ax, by plus ay. Okay, yep. We have what? Here, 3 plus 1, 4. 2 plus 3, 5. Simple enough. I like the method of components because it's a mathematical method that you can do easily in a mathematical fashion. Okay, here you go. Let's go get it. This one. Next, okay, you do the Pythagorean theorem, right? You want to find out the magnitude of C. There's just another method to find out the magnitude of C. You could find the magnitude of C using the cosine law, but you have to know this angle, right? And you can find out this angle, given what was given to you before. But the other way is just by using the components of the vector. 40 squared, 16, 25, 16 plus 25, right? You do the math. 25, 31, 41, right? Square root of 41. Yeah, square root of 41 meters. Okay, simple enough. One example. I am doing an example in which the vector is in units of length. But there are other types of vectors out there. There are other types of vectors as well. Not just in units of length, but in units of velocity, for instance. You're going to see that. Okay, here we go. Components of a vector. Subtraction between vectors. Okay. So let me get out a little bit here and let me get the notes. Okay, here you go. Operations with vectors, mathematical representation. We use that. That's my notes. Okay, here you go. You can write down vector A as having components in the x and y direction. Okay, another way of representing the vector would be, component of x in the x direction. This one now is a scalar, right? See that? What I have here is a vectorial representation. What I have here is a scalar representation multiplied by a vector. That's how we do it. Plus a scalar in the y direction, y hat. This scalar can be either positive or negative. It doesn't matter. Doesn't matter. Okay? Here you go. The scalar a sub x can be written down as the magnitude of a cosine of theta. And the scalar in the y direction can be written as the magnitude of a sine of theta. The projection, right? The projection of the vector in the x and the y direction. And if you sum two vectors, it's just like doing regular algebra. But the regular algebra applies only to those components in the same direction. See that? I'm summing A with B. A sub x, x hat, plus A sub y, y hat, which is the vector A. Then you have B sub x, x hat, plus the B sub y, y hat, which is the vector B. Now, if you want to solve that, what do you do? You can combine the x components in one part of the side of the equation. I'm combining the b sub x with the a sub x. See, this is a scalar multiplied by a vector. And then a sub y plus b sub y. If you want to know the length of this vector, you square this x component, you square this y component, and you take the square root. The negative, you subtract the vectors, okay? So is one component minus the component of the other, the respective component of the other. In both cases, component of the one minus the respective component of the other. Okay. Similarly, the x component is going to be the magnitude of the vector times a different angle. And whether you have a negative or positive is going to depend on the direction of the vector, right? Here you go. Let's see here. Here you go. In this case, see that? In this case, the vector has a negative component along the y direction. And I'm counting the angle in this clockwise direction. That's why I put a negative here. That's why I put the negative here. If I had counted the angle in this direction, then I didn't need the negative sign in there. Okay. Let me see if I'm getting everything that I want here. Effects, camera overlay. Ah, interesting. Not overlaying the camera. Okay, I'm going to move on. Okay, so here you go. Here's the magnitude of a plus b. That's the genetic equation. That's the genetic equation. What we did here in the board was a more specific case, right? Where ax and bx, we knew the values, the numerical values. But that's the most generic equation that for the magnitude of a plus b and the magnitude of a minus b. Okay. Don't forget what we see here is the Pythagorean theorem, right? It's the Pythagorean theorem. Here you go, the c sub x and the c sub y, right? Okay, and then you can do, okay, you can do a three-dimensional vector as well. When it comes to three-dimensional vectors, you do, now that you know the technique of components, of vectorial components, you do not need to keep on making drawings, but doing drawings is still important, okay? It's a little bit more difficult when we are talking about a three-dimensional vector. Okay. So a vector is given to be, the components of a vector is given to be this one. Component in the x direction is 2, 1, and 3. I didn't put any units in there. Okay, what's the magnitude of each component? That's easy, right? The magnitude of each component. 2, 1, and 3. Let's know. What about the magnitude of the vector? Okay, the magnitude of the vector. Let's make a drawing here. Here you go. 2, 1, and 3. Here you go. X, Y, and Z. Right? X component is 2 units. Here you go. So go ahead. 1, 2. 1, 2. Okay? So this vector has 2 units along the x direction. Along the y direction, it has only 1 unit. Here you go. Oh no, that's z. That's z. That's z. Okay. Right in here. And along the z direction is 3 units. 1, 2, and 3, right? Right there. Okay. So here you go. Here's the x component. Here's the y component. And here is the z component. I'm going to put an arrow there. And those vectors, they must sum up. Okay? Ax plus a sub y result in this one right here. And okay, and now I'm summing this component with the other one. I'm gonna put a different color. Is going to result in something like that. Ideally, I should be doing different colors, right? Let's do different colors here. Here you go. A sub x. Blue. A sub y. And I'll keep a black color for this one, A sub z. Okay, and that's my vector A. That's my resulting vector A. How do I get the magnitude of the vector? Just recognize. This one here is, let me get another color. I don't have another color. Leave it black. Yeah. I'll call this one A in the XY plane. Okay. The magnitude of A in the XY plane is A sub x squared plus A sub y squared. And the magnitude of the A vector is going to be the magnitude of A sub xy plus my square plus A sub z square. Okay, so what you get? Pythagorean theorem. Square so in the three-dimensional space, the equation is similar. Okay, so here we have another example here. Okay. Any questions? 532. Let me get my water here. Oh, cannot bring like that, right? Let me take attendance now. Daniel Abraham. Mario Acevedo.
Yes.
Haron. Atif. Musa. Genesis. Jennifer. Vincent D'Aloisio. Robert Faust.
Here.
Pedro Flores. Lawrence Flores. I just went out. Okay. Alexander Garcia. Sung. No. Brian Ejeda. No. Brian Inez. Athena. No. Jesus Lep. Cassandra Martinez. Dylan Martinez. Henry Martinez. Leonardo Melgar. Rafael Mercado. Raymond Miramontes. Jaime Mondragon. Alexis Nigret. Yahia Paris. No. Marco Antônio Partida. Armando Pérez.
Here.
Abraham Martinez Pérez. No. Nicolas Pisano. No. Hans Puskar. Ramon Quintana. Albert Ramirez. Joe Romero. Ali Shalabi. Okay. Anna Sieda. No. Dave D. Tom Patley. There. Antonio Vega. Kenneth Villagomez. Patrick Villavazov. Okay. Nolan Williams. Nope. Okay. And what about Jensen? Is he there? No, Jensen. Let's see how many students we have here. Okay. So let's have our break now. Any questions before I go to the break? Remember, the lab report's not due yet, right? Today I'm going to walk you through, today on Thursday, next Thursday as well, right? After the day after tomorrow in the lab, I'm going to walk you through how you're going to plot your data and solve some other things that are in the table, okay? But it's gonna be due today. The first lab is gonna be due next Tuesday for the Tuesday students, and next Thursday next week for the Thursday students. Okay. Okay. So let's have our break, 15 minutes break, and we continue. Six. Break.
Prof. Flores is here. Lawrence Flores is here.
Yeah.
Lawrence Flores is here. I think you
One
marked me
minute.
absent.
Let's see, Lawrence.
Yes, Lawrence Flores. Flores.
Flores.
Yeah.
Let's see here.
I went to the bathroom. I think that's when you called roll.
Yeah. Let's see, Lawrence. Yeah.
Okay. Yeah.
It's in there. Okay.
Okay.
Good.
Thank you.
Welcome. Let's take a picture behind me. Sitting down here, should I turn it on now? Should I turn it on? I forgot completely. And then I got involved that I completely forgot. Thank you, thank you. So here you go. Let me just, you know, record this, right? September 14th, 2021. What we're doing here, we are deriving the Torricelli equation from two of the equations that we found for uniform acceleration, right? Like I said, the Torricelli equation is not an independent equation, but it's a useful equation. So useful that we introduce that to you. If you know those three equations, you know everything about uniform acceleration. Okay? You know everything about the uniform acceleration. But, you know, because the Torricelli equation is so useful that you know, we introduce that to you, we show how we derive it. But remember, Torricelli equation is not an independent equation. It's dependent on those two equations right in here. Okay. So the idea is the following. Example, right? Let's treat that as an example. Using the second and third equations above, derive another equation that is independent of t. Okay? The Torricelli equation. Right? So that's the idea here. The idea is to get an equation that's independent of t, that does not depend on t. So we start with those two. Okay, and what do we want to do? We want to eliminate, we want to get an equation in which t doesn't show up, in which the parameter t does not show up. Okay? So how do we do that? In order to do that, we eliminate, we eliminate t by writing it in terms of the other parameter. Okay? There are two ways you can do that. There are two ways you can do that. Either you use, either you eliminate t using the equation below. Here you go, this one here. The equation for the velocity, okay? The equation for the velocity, okay? Or you eliminate t using the equation for the position. Okay? Eliminate. Which one is easier? It's easier to solve for t using this equation, or it's easier to solve for t using this equation?
The top one.
The top one, why is that? Because?
Because it's shorter.
Um, yeah, but that's not the real reason. Yeah, but why is better to solve for t using this equation at the top? Why is that?
It has less variables.
Because what?
It has less variables.
Less variables? No, that's not the reason. Oh, you hear that? Okay, here you have two solutions for t, right? Right? You have to get that whole mass of minus b plus and minus the square root of b squared minus, right? Divided by 2a. So here, no, here's a linear equation. Here's a linear equation. Here's a quadratic equation. Because it's a quadratic equation, the solution for t is going to be more complicated than the solution for t here. Okay? So whenever you're solving an equation, so just try to follow the easiest path, right? If it doesn't work, then you gotta go the next step. Use the something a little bit more complicated. So we solve the t using the for t using the equation for the velocity. Okay. There are two ways. You either eliminate. Okay. The easiest approach is to solve for t using the equation for the velocity. Or here you go. I'm gonna pass V naught to the other side, right? Becomes negative. Multiply and divide both sides. No, divide both sides by A, right? Divide both sides by A. Oh my, this computer is so slow. Okay, here we go. And I'm going to, you want me to do this step? Let's do this step, right? Yeah, see, this computer is kind of slow. Okay. We solve for t. We put t on the left side. Here you go. And then what do we do next? Okay. Remember I told you that we're going to use two equations, right? Next, we use the above solution, right? In the equation for the position. I remember doing that in high school, folks. I had physics there. I had a terrible professor, terrible physics professor. But we had to do that. There in Brazil, I used to have this professor that would arrive in the classroom, sit down at his table, open it, would tell us, do problems X in the book, right? Then he would sit down at his table, in his chair, open his newspaper, and kept on reading the newspaper the whole class. He would do anything. You know, one day one of the girls got pissed with him, and he just said something to him from the whole class. The guy was so embarrassed. Because one of the girls, not one of the boys. Nobody, none of the boys was willing to embarrass him in the classroom. But think about it, the professor that's come to the classroom just to read the newspaper and don't do anything, right? Not nice, right? Here you go. But how do we do it? The solution is like that. We get this one, we substitute in the equation for the position. Here you go. And substitute here for t. Oops. Oh, I did it the wrong way. Okay, this one goes right in here as well. And then I gotta put the parentheses here so you know everything is moved. Here you don't need the parentheses, right? Here there's no need for the parentheses. But in the other one you must show the parentheses in there. So now we go ahead, copy and paste. Now I'm gonna distribute the V naught. And here my V naught is gonna become V naught square. And I have to expand this guy. This one's gonna become a square. Can you do that? Try to do that without looking at what I am doing. If you can do that without looking what I'm doing, that's because you're good in algebra, right? We go v square, and then I'm gonna have a v naught square, but it's going to be a positive v naught, not a negative. And then I'm gonna have the cross terms, 2v v naught. But it's gonna be a negative sign because it's v minus v naught square minus 2v minus v naught, like that. Don't forget. Ooh, I'm running out of battery here. Let me get my power. Great. Okay, what's next? What can I do next? What's going on here? Oh, why is marking like that? Okay, okay. What can I do next? I can cancel out here, right? A with A. Okay. Maybe let me see if you're having any problems understanding. Maybe I should put one more step here, right? Let me put one more step here in case you're a little bit lost. Yeah?
I don't know, maybe I'm not done. You mentioned that V naught for A on the first fraction.
Is here?
Close to the third one.
Third one?
Third equation that
here?
you have. Yeah. You know how you distributed V naught to the first one?
In this one?
Yeah. You mentioned the V naught on A.
In this one right in here?
Yeah.
Think about that. I am distributing the V naught, right? V naught is going to multiply with V,
yeah.
Right? So I did that here.
Yeah.
And then V naught is going to combine with V naught. It's going to become V naught square.
What about the A? You're not, you don't multiply it
A is here, right?
So you don't multiply it with the V naught?
No, the A is being divided, right? So you don't multiply the A, right?
Okay.
The A is downstairs. So this V naught here is, remember, this V naught is what? This V naught is something like that. It's V naught divided by 1, right? That's what it is. The 1 multiplies the A, yes. But the V naught only multiplies each of those parameters here. Okay?
But you did here let us work the A square for the second part?
You're talking about this one, right?
Yeah.
Okay, let me finish here first. Let me finish this one here first. Here. And, okay, so let me put the square here. I'm going to put it this one. And you understand that the A becomes squared, right? Because it's the parentheses. Let me put that here. And now I'm going to simplify that. I'm just adding a step. Okay, here you go. Right? So here you go. Now we do not need that one here anymore, right? I can take out this one, right? Okay, here you go. Okay, so what's happening here? We have A and A square, right? A divided by A square, right? So this A is going to cancel out with this A square here. Okay? Make sense? Right? So what you have here is the same as this one here. Here you go. The A is multiplying the numerator, right? Here you go. And the 2 is multiplying this A square. Right? That's what we have. That's another Okay? That's what we have. Right? And now we can cancel this A with this A. And that's why, and that's why, let's see here. Let me get this one. Let me put this one right in here, right? Okay, makes sense. No secret here, right? A cancel out this A, so we end up with only one A downstairs. So here you go. I'm gonna do like that. This one disappear, and we are left with just one downstairs. And now I can expand what is upstairs, right? V square plus V naught square minus 2 V naught V. I'm putting the half back where it was. But if I want, I can, continue with the 2 right in here. Okay, now compare those two fractions here. One is divided by 1a, the other one is divided by 2a, right? So we may combine them provided they have the same denominator. Let's put them in the same denominator. We have a 2a downstairs here. So let's put 2a here too, but let's make sure that the equation doesn't change by multiplying above by 2 as well. Right? I'm dividing and multiplying by 2. And now I can combine those two fractions because they have a common denominator. Okay? That's... So let's combine here in the same numerator with the same denominator. Here we go. I don't need that other term anymore. Okay. Now you can look what simplifications you can make. You have 2v naught v here. Do you have another 2v naught v? Oh, yeah, you have 2v naught v.
They both cancel.
They cancel, yeah. They cancel out, right? So I'm going to put in a different line. But we also have minus 2v naught square and v naught square, right? What do you end up getting?
You get 1v squared.
Huh? Minus v naught square, right? Minus 2 plus 1, right? So minus v naught square, I get rid of that. Here you go. And then we are almost done. We usually write this equation in the following way. We pass the x naught to the other side. Subtract x naught from both sides. Right? Multiply both sides by 2a. Okay, good. Multiply both sides by 2a. And then pass the v naught to the other side and sum both sides with v naught square. Or, pass the v naught to the other side. Okay, so we usually write that with the v square on the left side, and we put the v naught square before, which way x minus x naught has a name, right? How do you usually denote x minus x naught? Delta x is the displacement. Displacement. We go delta x. Go like that. That's the Torricelli equation. Again, this is not an independent equation, but it's still useful. Okay, if you want to find the final velocity and you don't have the t, but you have the acceleration, the delta x and the v naught, you can use this equation here. Okay, save it. Digest it, right? A little bit. If you think this a little overwhelming, that's because you gotta do that over and over again to get familiar with. Any questions? Okay, so to get something like that, you gotta know your algebra, right? You have to know your algebra. How many lines? Let's see. Wow, quite some, huh? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 lines. A lot, right? 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Yep, 15. Oh, actually 16 because I still have this other one, right? 16 lines. Okay. It sounds lots of work, but one of the simplest derivatives that we can do. Okay. So that's what I want to show to you before moving to the two-dimensional motion. Okay. Save it. And let's take a look at physics node. Okay. Let me get the PowerPoint here. We did that. Yep, we did that. What's that? 1D motion graphs. 2D motion graph. Okay. Now let's start with 2D motion. Two-dimensional motion. Okay. So in order to describe two-dimensional motion, what do we need? You need the x and y axis, right? So let's start with the x-axis. The origin is around here. You put the y-axis, and then what do we do next? Okay, we're going to consider what we're going to do now. So what we have been doing so far? So far we have been studying only one-dimensional motion. This is one-dimensional motion. This is one-dimensional motion. Okay. What we're going to do next? We're going to study two-dimensional motion. Okay, the motion of an object in a plane. Here is an example of two-dimensional motion. Okay, that's what we call a projectile. Here too is a motion in the two-dimensional space, and then you can have three-dimensional motion, right? So before we get to three-dimensional motion, we do one-dimensional motion because it's simpler, but not just because it's simpler. It's going to be easier. It's not easier, right? You see, it's not easier, right? If one-dimensional motion have those equations, that doesn't look like easier. Imagine two-dimensional motion, three-dimensional motion, right? So first you get used to one-dimensional motion, and then we move on to something more difficult. Always starting from the simpler to the more complex, right? So here you go. In two-dimensional motion, you need the x and the y axis. Okay? Three-dimensional motion, you need the x, y, and z axis. Here you go. Here's a particle located in the three-dimensional space. But let's go back to two-dimensional motion, okay? X-axis, y-axis. Let me do it this way. Here you go. Better, right? And here you go. Let's say a particle is describing this path in the two-dimensional space. The most generic possible, okay? So at a given instant of time, the particle is here, later on it's here, 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 and so on. Okay, so here you go. Here my particle represented by that dot. And what do we do in two-dimensional motion? Okay, we represent the position of the particle with respect to the origin of your axis. And we represent the position of the particle by using what? What's this guy writing here? It's a vector, yeah, using a vector. It's a vector position with respect to the origin. And I even gave a name to this vector. I call it R0. R0 is standing for initial position. See the arrow here at the top of the R? Okay? So at a given time t equal to 0, this particle is at this position. Okay? Time t equal to 0. T naught equal to 0. And has coordinates. Okay, the vector R0 has coordinates x0 and y0. Here's another way of denote representing a vector. Here's another way of representing a vector. X0, y0 between parentheses. Okay. Here's a shorthand, right, for a vector. And here you go. We can write our vector as a scalar x0 in the x hat direction. See about that? Do you see that? Here you go. Here's the x component of my R0 vector. Do you see that? Can you picture that in your mind? I didn't picture that here in the drawing, but the x0 x hat is this vector right here in the horizontal direction. And the y0 y hat is this vector here in the vertical direction. Okay? But, you know, and the particle is moving along this path. It has a final position denoted by this other vector. Okay, so the question is, what is a vector? Okay, what are the quantities that are vector? Well, position is one possible vector. Okay, position is one possible vector. You're going to see that there are more. There are more vectors. Here we go, vectors in physics. Vectors in physics. Well, the first one is the position vector. Let's put in the other one. Yeah, I'm gonna put in the. Here you go. Vectors in physics. Position. Position is a vector. There are more, but let's start with this one first. So now we can go back to that our very first slide. Okay? Remember? Let's see here. Oh yeah, right in here. The building blocks of physics. We can correct one of our primary definitions. Okay? And even more important, I'm going to tell you right away, all those 7 basic quantities are scalar. Have you ever seen length as being a vector? Time being a vector? Time has direction? Mass has direction? Right? It doesn't. Right? So all those quantities, basic quantities here, they are scalar. But the primary definitions, they are all vectorial quantities. Okay? So now I can put, instead of x, I'm going to put r with a. Do you see the difference now between the primary definitions and the basic quantities? The basic quantities are scalar quantities. The primary definitions are vectorial quantities. Okay? Fits nicely, right? To emphasize that they are different. Oh man, this computer is so slow. Area of a circle. I miss my big computer there at home. I'm thinking about starting recording all those classes there at home in my big computer and then post there in the YouTube, right? And then we come here. I'm thinking about doing that. And then we come here, we discuss what's there in the recordings. What do you think? Okay, I'm thinking about doing that. Let's see, where is the accent? See how slow it is? My big computer there at home is not slow like that. Oh man. And it's a new computer. I don't understand why it's so slow. I believe the double over. No, that's not what I want. Where's the arrow? That's the arrow finally. Okay. Come on, man. Yeah. Position and force. Force is also vector, okay? Force. Measured in Newton. Position is a vector. And now we can have, from current slide, we go. You already saw the initial position vector. That's the final position vector. Okay? And now that you have the initial and final position vectors, you can realize that there is also the displacement vector. Just like we had in one-dimensional kinematics, right? Just like we had in one-dimensional kinematics. X final minus X initial. But here's going to be R final minus R initial. See, think about that. See the head-to-tail method here? R naught plus delta R is equal to RF. Can you picture that in your mind? Head-to-tail method. R naught plus delta R is RF. Okay? We are applying what we saw mathematically, right? So what's next? Okay, here you go. Here is my how this called we did the head to tail method, and now I'm showing you the parallelogram method, right? I'm showing to you the parallelogram method. Here's the parallelogram method that is used to find the final position vector. Okay. Okay, and what's next? What's next? So, in one-dimensional motion, we talked about position. Then I defined the displacement, right? Then I defined what? The average velocity. We do the same in two-dimensional motion. Okay? And how do we define the average velocity vectorially? Here you go. In a scalar fashion is delta x over delta t, right? But in vectorial fashion, it's still going to be the same definition. It's just different letters. Delta r over delta t. Because delta t is scalar, because delta t is a positive scalar, the average velocity vector is going to have the same direction as the delta r vector. Just like you see right in here. See that? Average velocity vector parallel to delta r. Too much? But no? Are you follow? Okay, here you go. Here's the delta r. It has a x component, it has a y component. Here's the angle with the x-axis. Okay, and here's the average velocity vector. Yeah, here I'm illustrating. Okay, don't forget, I can denote the average velocity vector either this way or this way, okay? They are the average velocity vector with respect to delta r, they are different quantities. So it doesn't matter if you denote it this way or this way. They have different units. This one, what's the unit of the average velocity? What's the unit of average velocity? Meters per second. What's the unit of delta r? Meters. So it doesn't matter if you denote the average velocity with this shorter arrow or this longer arrow, provided, of course, you state that 1 meter per second is the length of one square. Okay, so that's what it means. Delta r parallel to average velocity. Now, what we are going to do? We are going to find out what's next. The instantaneous velocity. Okay. And the question is, how can we illustrate the instantaneous velocity vector in this xy plane? Okay. Well, the way we do exactly how we do in the one-dimensional case. We make delta t goes to 0. As delta t goes to 0, delta r goes to 0 too, right? So I'm going to get points that are closer and closer to the initial position. Okay, so here you go. Instead of this point, it's going to be this one right now. They're going to, oh, here you go. I want to know, oh, wait a minute. I want to find out the instantaneous velocity at this point. That's what I want to, that's what I want to find out. Okay, and so what are we going to do? I'm going to decrease the delta t between the initial and the final position, which is going to lead to delta r smaller and smaller. See that? So if you do a careful investigation, what do you find out? We find out the instantaneous velocity will always be tangent to the path of the particle. Okay, no matter what the path of the particle is undertaking. If this guy is described as a parabolic path here in space, it means the instantaneous velocity vector will be tangent to this parabola. Okay, can you remember that? It's possible to prove that. Okay, here you go. So here, the velocity, instantaneous velocity at this point, the instantaneous velocity at this point, the instantaneous velocity at this point. I do not know the magnitude, but I know the genetic direction. The qualitative direction of that velocity, instantaneous velocity. Let's do that again. Here you go. This way, right? Until you realize that's tangent to the path. Okay. And how do you do that? There's a nice way of figuring that out. Okay. The average velocity. Well, let's see here. The average velocity vector is what? Delta r over delta t, right? So delta r over delta t is what? Is delta x hat plus delta y hat over delta t. Right? Or delta x over delta t, delta y over delta t y hat. Okay? So let's see if I have it here. Yeah, I don't have it here. And let's see, the angle. Yeah. So the angle that this vector makes is going to be what? Is going to be delta I, delta y over delta x. That will be the tangent. Okay? But it's going to be in the limit as delta x goes to 0 and delta y goes to 0. And this thing is what? dy dx, which is exactly tangent to that path. Okay? That's how we figure that out. That's how we figure that out. So going back here, here you go. See the angle? The angle of the average velocity vector is what? The tangent of this angle here is what? Is delta y over delta x. As delta y over delta x goes to 0, okay, we get a direction that is the direction of the instantaneous velocity vector. But as delta y divided by delta x goes to 0, as delta y divided by delta x, as delta y goes to 0, as this ratio goes to 0, delta n delta x goes to 0, this thing is equal to what? dy dx, which should be a tangent to the curve. Okay, so that's how we figure out mathematically. Okay, and here's the representation. What time is that? 6:40. 10 more minutes to go. Okay. Let's see what we're going to do now. So let's go to the notes here. Position vector. Here we go. Average velocity vector. Instantaneous velocity vector. Always tangent to the path of the particle. Okay. So we got position 1, 2, 3 vectors. We have 3 vectors so far. 4 with the force that we're going to cover soon. Okay. Let me see what's going on here. Okay. Okay. Here you go. Let's see here. Okay, so what am I saying here? I'm saying here that a two-dimensional motion, like this one, is nothing more, nothing less than a combination of two independent motion along the x-axis and the y-axis. That's what I mean here. Okay? If you combine the motion along the x-axis with the motion along the y-axis, you get a two-dimensional motion. That was what it's all about. That's what this graph is all about. Okay, so in the next step, I want you to find out what would be the qualitative direction of the average acceleration vector between points 1 and 2, 2 and 3, and 1 and 3. Try to figure that out. Okay, you already know what's the definition of the acceleration, right? In one-dimensional motion. Since you know what's the definition of acceleration in one-dimensional motion, you should know also what's the definition of acceleration in the two-dimensional space. Right? Here you go. Now we're talking about average acceleration. Average acceleration. Which is going to be delta v over delta t. Okay? That's the next quantity. Now, looking at this definition, try to figure out what's going to be the genetic direction of the acceleration vector, of the average acceleration vector, between points 1 and 2. Try to do that. Let's see. That's 6:42. I think there's time. We have 8 more minutes to do that. See if you can do that. Okay, here you go. Here's the definition. Oh, here's the definition, right? Delta V over delta T. I wrote that down there for you already, which is final velocity minus initial velocity divided by delta T. Note, see that the average acceleration vector is parallel to delta V. Note, see that. That's a very good clue to find out what would be the direction of the average acceleration vector. You pictured that already? Remember, I don't want the exact length of the vector, but just the generic direction. Here you go, qualitative. Okay, here you go. Here you go. When you subtract two vectors, it's actually summing the negative of another vector, right? I shouldn't have done that. Let me take this one out. I'm gonna put, I'm gonna put like that. I'm giving you the answer without allowing you time to think, right? Better now, right? Now from current slides, here you go. That's V2 plus minus V1, right? So look what we get. We get this generic direction here for the acceleration vector, okay? Which is parallel to the average acceleration vector between those 2 points. Now note C that the average acceleration vector is pointing towards the center of curvature of this path. That's no coincidence, okay? There's no coincidence. The instantaneous acceleration vector always points towards the center of curvature of the path, always. The average acceleration vector may not, because it's going to depend. It's going to depend what's going to be the points that you're getting. Okay. Then you can do for the other ones between point 1 and 2, 2 and 3, and 1 and 3, right? Did I do for that? Let's see. 1 and 2, the 3, okay. Now we're doing between 2 and 3. Between 2 and 3, they are almost parallel to one another. They're almost parallel to one another. That's minus V2. Okay. It's gonna be in this direction. The average acceleration vector is a point somewhere between here and here. Okay, that's what the average acceleration is gonna be, anywhere around here. These 2 points somewhat in the direction of the curvature. And the other one. Okay, if you want to denote more or less what's gonna be the direction of the average acceleration vector, like I said, it's gonna point somewhat towards the center of curvature. Okay. Here at this point, the average acceleration vector and also the instantaneous would point in this direction. Here too, another average acceleration vector, and so on. Here you go. Okay, let's see if we have more. Yeah, let's stop here, right? Otherwise it becomes too much for you. Let me write that down here. Average acceleration vector now. average acceleration vector, and then we have instantaneous acceleration vector always points towards the center of the curvature of the path. Okay, this one does not necessarily point towards the center, okay, but the instantaneous does. Okay, so let's see this guy. I wanna put it here. Any questions about that? Okay, so let's go upstairs now, right? And I'll see you on Thursday again.